Hi, my name's Bob Greenyer, and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for joining me this 13th of November 2022, when we will be discussing the VEGA pillows. If someone can tell me if you can hear me, that would be a great thing. Okay, great. And I guess the question remains, can you see me? Can you see me? Okay, great. So I'm going to go back to the holding frame. I'm just going to check I have a mobile camera working. So give me a second. Let me just change the view in OBS here so that I can see what I'm about to bring up. Boom, 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 boom. Studio mode. Okay. Copy. Another one. Okay. And paste. Okay. That seems to be working. Okay. Okay then, so we are going to be looking at the VEGA pillows. And what do I mean by that? I mean this object that you see here. And I'm going to try and do this. You can see the kind of scale it is. And they are still just about attached. Now, this was sent by UPS by Henk Jurrien to me, having seen it. It is still attached, Henk. Trust me, it is. But it's nearly not attached because having transferred itself once to me and not getting to me, and then being sent back to Holland, I then went to Holland to set up a recording system for Henk so that the replication of this can be conducted with recording and other experiments. So I can change the focus pull on this. So focus on the near field there and focus away. And you can really see the kind of scale of what's going on here. And this is going to become very important. Now, this is 2 brass plates, and I have measured those with this pair of calipers here, and we might do that live on camera in a little bit here. But the thickness is 0.75 of a millimeter, and that's going to become very, very relevant in a little while as I explain how I believe this has been able to be achieved. Okay. So yes, I think these are going to fall apart, but I am going to be looking at these inside and the outside under the SEM hopefully soon. But you can see that clearly the top pillow here is not, I repeat, any more 0.7 of a millimeter thick. It's very much thicker than that, you can see down here, compared to the one on the bottom. Okay. Interestingly, it's like it's piped all the way around the outside, and we'll see this on some of the Dynalite microscopy in a little while. And yeah, so there we go. It's like sealed all the way around the outside. And I think what we found on the VEGA alum sample, this one, explains it. Now this is approximately 3 millimeters, this particular sample. And that 3 millimeters is not 0.75 of a millimeter. And that, I believe, is very important. But as you will see when we look at the images, what we found is that these little black spots everywhere where we see these coulombic explosions from these fluidized electrons going to an EVO launch point, having now replicated those observations of Kenneth Shoulders. When you get to the boundary here, you might even be able to see it on this image here. I don't know. Let's see if we can zoom in. Maybe it's even clear on here. I don't know. Can you see it's kind of slightly lighter along that edge there? Well, what we found was when we were looking at this under the microscope is the number of these black spots peters out to nearly 0 along the edge. And I believe this is due to the fact that the EVOs can't form a sufficient launching point there. They do it inside the boundary more. And this leads to the edge being affected very, very differently from the flat surface. And this is more of the same of the kind of concepts that I was talking about when you are looking at spheres and torids with minimum surface curvature. Obviously, this has got a lot of surface curvature. It's a 90-degree point. And so you might get an EVO forming on the edge, but you don't get the actual explosion forming within a boundary of the edge, it would seem. It's much rarer. And I think that has followed through to why this is effectively sealed around the outside. Now, why didn't the aluminium blow up? Well, firstly, it was aluminum on aluminum on a steel plate, whereas this is brass on a brass plate on a mild steel plate. And you can see very, very clearly that the bottom plate is not affected in this. In fact, if we turn it over in a minute, and it probably will fall apart finally when we do that, you'll see other than a few spots underneath, it's really the clean brass with no really affected area under that. Okay, so this is the thing. Yes, I think this is, Corky, a Hutchison effect, and I think we can prove that today in this stream based on a Hutchison effect sample, what we've learned about those samples in the past, and lion experiment and so forth. In fact, they are my next couple of slides. So the exciting thing about this is, and I will share these videos in the coming days, is that a experiment was built to replicate this, and it worked first time. Slightly different. This is the same copper plate. It was put on another, brass plate, put on another brass plate. But as you can see, it has pillowed up. Not quite as so dramatically, but it has pillowed up. And also there was an explosion here. And we're going to look into this explosion, and that's going to tell us some information about what is going on, as is the surface of the pillow one. So this is, in my view, it is a EVO-based phenomena. We have the signatures of the EVOs. You can actually see the little balls on this one that we have observed in other experiments, this kind of balling up that you can see here. The balls aren't actually on here, but some of the videos that I shared today that Henk produced show the same kind of ecton, George Messiat's name for EVOs, occurring around the base plate here and around the mild steel. But what we've done actually in Holland now is we have this streaming set up, and he can stream to the MFMP YouTube channel. And he's actually got a square brass plate the same size as this, and he's cut a round disc. So the idea is, can we create a round cushion? And I believe that if it doesn't happen first time, it's going to happen pretty soon. But this is a highly unusual and a unique observation that Henk did. And like I say, that bottom plate there is 0.75 of a millimeter, and so was the top plate. But now the top plate is clearly not as it was originally. Okay, you can see it there next to my fingers. That is definitely not 0.75 of a millimeter anymore, that top plate. In fact, it's nearly as tall as my thumb. Sorry, my index finger. It's very fat. Now, one would say, why didn't this melt? I think that what you're looking at here is equivalent to a jellification. It's jellified. And as a result, it did not melt. So we can pull the focus on this. It's quite flexible. I'm using a Talis NDI camera with OBS Studio plugin. If you want to know how I'm doing this, I've used it before, but you can see the pillowing here is not quite so extreme as the original. However, it definitely exists, and this blowout, again, like I say, is going to tell us some more information. Look at the underside of this. It's essentially not affected, really. Okay, I mean there is clearly one of these magnetohydrodynamic effects going on there, and some of those kind of trails that you see in the Vega Valley coming out from that. And there's also a split area here, and I think that's where there was a blowout from this, and similarly there was a blowout from this. I'm going to try and turn this over. This might be the moment. I'm sorry, Henk, if it falls apart. This might be the moment that it does it. Let's see if it still stays together as one piece. No, it's finally gone, and actually that's quite good, because you get to see that for the first time as I do. Now you can see here, this is the underside. There's just a few spots on there, but other than that, it's pretty much similar to just a flat sheet. Okay, so what are we seeing on this for the first time? Because Henk's not seen this, and we had to break it up anyway sooner or later in order to do the analysis. So here we go. This is what we are seeing. You are seeing this with me live for the first time. So that is what it looks like. So there seems to be a very clear spot there in the center, and this area around the outside where you've got this maybe copper oxide, or maybe there's some carbon in there, I don't know. Things that look very coppery or brassy. Okay. And then on the back side of the pillow, which we've never seen before. Oh, look at that. Oh, that's quite fine, isn't it? Look at that. Wow. That is a work of art in itself. And in fact, what I'm going to do, actually, I'm going to take some beautiful Sony Alpha images of that, because that is, in my view, a work of scientific art. Well done, Henk Jurrien. So, what does that look like? It looks like, what has happened there? Let's have a close look into that. I'm really quite excited that, you know, I would like these things to have stayed together a little bit longer, but, you know, things happen. It had to be taken apart at some point, but look at that. Wow. So, have I got something I can point with? I've got a screwdriver over here. I've got a big rubber thing. That might be easier for me to point with. So what we've got here is we've got what appear to be some Evo marks along here. That's a not very clean thing. I don't want that close to that sample. Right. So you can see here, this is a standard sort of kind of Phillips screwdriver. This is quite a lot fatter, even though it started off as 0.75 of a mil, than the original sample. Okay. And yeah, so let's move this around. Wow, what a beautiful thing you've made, Henk. Let's just pull the focus plane. There you go. It's literally like a throw cushion, isn't it? That's kind of exactly what it is. It's a throw cushion. Okay, how can we do this? I didn't bring my tripod in for the camera. That would have been a sensible thing to do had I been thinking a little bit more ahead. But Yeah, look at this. Look how fat that is compared to this screwdriver head. Look at that. It's significantly fatter. Again, there seems to be some focal point there and another one down there. And you can imagine the EVOs going around on that. Now, can we zoom in any tighter than we already have? I don't know. Let's see. That'd be a yes then. Right. This is when shaky vision comes in. Anyone feeling sick yet? Okay, all right. I'm going to zoom it a little bit out of that because that's too shaky even for me when I'm doing it. Right, so I'm going to have a 5 times zoom here. How about that? 4.9. Okay, and we'll try and focus that. There we go. So look at that. So there seems to be some sort of Vega valleying type structures down there in that little bottom end there. This contact, and that might be a contact point, and there might have been an EVO swirling around there, a large macro one. Again, more of the same here. And then there's this edge. Now that edge, actually, what happened was, if you look at some of the videos, you can see that when this thing puffed up and moved off to one side, it kind of like fell down onto the iron. So this actual bit was in contact with the iron. So if there's any iron there, there's no surprise because it was in contact with the iron. Okay. Now this is interesting. This actually has this kind of bleed out. Now, can't work out if that's... I don't think it's melted. I think it's, well, I don't know. Look at what we got there. Are we looking inside that? I think we are looking inside that. I'll do a focus pull on this. There we go, that's the edge. So you can see how this is stitched along the edge, and on this edge it's kind of really rather round. Look at that. You can actually see where the original 0.75 of a mil edge is. Pull the screwdriver in here for comparison. Okay, that is breathtaking to me. It's one of the most interesting things I've studied since the original Lion experiment and several Hutchison samples. But this is not melted. This is turned into sort of a gelatinous sheet, a bit like the indium that was exposed to a Marsa gas. Briefly, it became this rubbery sheet, and that was only 75 microns thick. This is 75,000th of a millimeter. So this is 0.75 of a millimeter. So this is 750,000ths of a millimeter. So it was 10 times thinner, that indium sheet. It was as thin as a human hair, but it turned to like a rubber sheet and flapped around, and it glowed incandescently before it actually started to melt. And it only has a melting point of 156.6. Obviously, copper has a melting point of something like 60 degrees centigrade, 185 point something degrees centigrade. And this has not melted. It's not melted. And presumably, if we were to assume that these two halves are the same thickness, if it started out as 0.75 of a mil, then these are what, 0.375? What is it? 0.375? 375 microns thick each side of this pillow. It's remarkable. Absolutely remarkable. Remarkable. Well done, Henk. This is what can happen if you just try experiments. You know, you're not worried about everything looking totally fancy. You're just going, what happens if I do this? And of course, yeah, look at that. You can see how it's kind of like pinched down the edge. And this is what I'm saying is the field emission, the space charge around the edge is very different to the bulk surface area. the space charge of the bulk surface area is very different. And that is what you observe on the aluminium here, on the edge of the aluminium. This space charge leading to this kind of like, you can see it's dense and then the edge is kind of a little bit whiter. It's a little bit whiter down this edge of this 3mm segment here, section, okay, on the VEGA alum cathode there. Okay, so that's that. So I'm gonna just, I'll pull in the replication. So the replication is here. This is the fat part of that. And if I go over here, wait, I'll try and get that in focus. Right, so we are looking at that, and that is as thick as this typical Phillips screwdriver head. Okay, that's as thick. It has this blowout here. That's the edge on this. You see, it literally, it's just amazing. This is, did it once, first time attempt at a replication, it was a replication. Okay? That's what you call science. Now this is where the blowout happened. You can see there's a couple of other points there where there's some blowout. This is the surface with that sort of like Vega Valley streams going on. And then we turn it over. And you can see here. So, look at that. It's quite beautiful, actually. Blowout. So, you can see here with the, don't want to contaminate it, but you can see here with the screwdriver head, it's kind of like bigger than the head of this Phillips screwdriver. And I'll give you the scale for that in a second. Okay, I will just do this. Okay, and that is, oh dear, what is that? The hole there is 4 point something millimeters. Have I got it still there? 4 point, oh, really bad, 4.4 millimeters. Okay, I'm going to zoom out of this and I'm going to try and just do a couple of key scales here. So we'll zoom out of that. Right, so we've actually got, is there any way I can hold this? It'd be good if that would work. That would be great. There we go. Look at that. Right, okay. Let's see if we can. Okay. Maybe this will work. Okay, right. So first up, I'm going to measure the thickness of this plate here. How can I do this? Oh dear, this is not good, is it? Okay. That helps if I zero it. Zero. And, oh dear. Not the right camera set up for this today. And that is, as I said, 3 millimeters. Can you see that? That's 3 millimeters. Right. And we're back to 0. And I'm going to take the bottom brass plate here. And which area do I not want to affect? So that's the back of the bottom brass plate. And that is the top where the pillow was formed. And I'm going to measure it like from this end. Measure it like that. may be wrong actually, it might be 1 millimeter thick. Or my calipers are not working properly. Okay, it's saying, if I can get that upside down in camera shot, 0.76 of a millimeter. So yeah, I think it's 0.75 of a millimeter is the thickness of that brass plate. Okay, so that was sitting on there, so you can see how that piece goes on there, and that was what it was attached with, like so. That is the pillow, and that is the pillow replication. Right, so let's start delving into why this might have occurred. Okay, so I'm going to switch back to the frame here. Maybe, in theory. Ah, it works differently now because I've got it on that mode. Okay. All right, so there we go. Yeah, so why you might be thinking, oh, this doesn't, how should we put this? I'm going to change back into the normal mode because it's quicker. So what I'm using is I'm using a phone here, and the phone is sending a video feed through Wi-Fi to the over the network to the computer, and then that's broadcasting to you. So sometimes you have a lot of drop frames, but hopefully you've got enough there to understand what we are looking at. Okay, so let's move those over there, and we can do a little bit of discussion. We can look at some microscopy, and then we can see how this might play to Ken Schilder's observations, and it's all very exciting. So I think first up is the Vega Valley here, and this was effectively the inspiration for it. So same kind of configuration where you have a brass plate below and a brass plate above, and in fact in the Vega Valley case we had two brass plates above. Henk arranged it. In fact, it was at 3 actually, or so above, but it was only this these two in which the fluidized electrons were produced in abundance. And if you think about it, when you've got two non-perfectly flat striated brass plates contacting with each other, you're going to have a lot of different resonant cavities in there, and you're effectively with field emission and those resonant cavities going to do what is in Lockheed Martin standard coherent matter wave generation patent. And because you're effectively going to have these resonant cavities that are able to promote the coherence. And this is the top side, and you can see the balls of plasma here, which we know a lot more about, having been able to look into them since. This is the anode here on the right. And we know that you can get self-organization and double layers on the anode, but the actual ectons, the exotic vacuum objects, are born on the cathode. Okay, and having this gap allows for several resonant areas, and you saw on the anode of the Vega alum experiments, there is this regular spacing, so you can see that there are resonant areas for the fluidization and launching points to occur, and you can imagine over a period of time, and this was in the experiment for about 100 hours, so it built up these fluidized electrons, they moved down the channels, and this is kind of like a couple of frames there, so you can see how it was, you know, bistable or semi-stable when it was running. And underneath these two plates, this is the underneath of those two plates. If you flip these over like I did the pillow just now, you would see this. And underneath this was the Vega Valley itself. which there is a cross section here. And we established by looking at this and referring to the macro photography of Lyndon Gledhill using the ferrofluid, that the ferrofluid forms these polygonal cells on its structure with these points, and this is the gap in between, and this is typical of a magnetic fluid. You get this structure, and even with these zones like this and zones like this and all of these things like this zone like here and this zone like here are the same. So this is definitely a magnetic fluid, and we know it has these sort of conical structures on the walls. The interesting thing is, so I think Henk was going for something similar by having stacked brass like the Vega Valley, but just kind of like reducing it down to its simplest form. And this was a piece of serendipity. It was unexpected, but I think we can explain it. And it also probably helps explain a good number of Hutchison effect things. Now, why do I say this is Hutchison effect-like? Well, firstly, the Hutchison effect often is a surface effect, and unless it can get right the way inside, and then it does things on the inside, or the structure gets so big that it's affecting, there is a point of, I guess the US Navy would call it space-time curvature singularity. Anyway, I call it a focal point for cold neutrino condensate. But anyway, for instance, the coral twist, most of the affected area is within a small fraction of the thickness of the outside of the material. It doesn't appear to be affected on the inside, but when you try and analyze the inside of that cross section of the coral twist, you find that the elements do not report ordinary element spectral lines. And I believe that this is the toroidal moment of the surface bound, and we know the EVOs stick 50% into and out of a metallic surface, because we showed that on the Hutchison crystal, the fracture sample. So that's how I derived the fractal toroidal structure. You can see that it embeds itself part the way in and part the way out, and you can understand that it's because aluminium, for instance, is paramagnetic. It is going in and it's centering on the center of the vortex structure and the subvortex structures, if you know what I mean. And so it stands to reason that it would sit kind of half in the surface and sweep material through the center, as we saw in the various scales of those yin-yang structures. Firstly, the innies and outies, the yin-yangs at the small scale, but as it got bigger, you just saw one which was a cluster of the, like a yin or type or a yang type, it doesn't really matter. And you see the sweeping of the spin nuclei, 27 aluminium, around the outside. So this shows that it binds to the surface, but it's like I showed in the ultra experiments. As it's producing that pit with a cone, it's sweeping like this, burrowing into the surface until it reaches a point of stability. But the toroidal moment goes out in front of it, and that will be pulling the dark matter through to a central point. And the central point in that case would be kind of like partially in the surface if you then had a mesh of these things. And this is where the key point comes here, is that we are talking about a mesh. And Ken Shoulders said that these things can enshroud things, they can cover them. Okay, and here it is on the Hutchison fracture sample itself with innies and outies, these yin-yang things. You can see the polygonal things and the semi-regular array that is forming a thing coating the whole surface. Okay, and it can be more ordered on the large flat area, but it gets a little bit more wonky on the edge. Okay, this is on the Lion jewel, and we know that this is very, very interesting because the jewel was encapsulated in this, in the shape of this particular shape, which we know is the Eye of Ra, Eye of Horus type shape. And so it's protected from the effects that caused, with all of the same parameters, the same Cantal heater wire on the outside, the same core of the reactor on the inside. This was totally differently affected. It doesn't have this green all the way through. It has this white layer, and then it has this rose quartz. And the way you get rose quartz is you heat up quartz to a few hundred degrees, like 400, I think it's 650 degrees or something like that. I've talked about it in the past. You can go and look at a previous presentation. And then you have to have affected it with I think it's beta radiation or gamma radiation, something like that. You use a cobalt 60 source, so it would be beta and gamma. And that allows you to convert, say, for instance, ordinary quartz that you might get from a quartz deposit, and convert it into rose quartz that can be used as a semi-precious gem. So we know that this had to have been produced with heat and radiation. And we know that Ken Shoulders said that EVOs blowing up release electrons at high velocity, which are effectively beta particles. And Shishkin has observed those up to 10 kilo electron volts, and that would be suitable. And that it can also produce soft X-rays, and something like 2 kilo electron volts. So it has the ability to and do what is necessary to create this effect. Okay. Now we know when the impact to surface that interesting things happen in the center of these things, and this is seen all over the Hutchison sample here. Okay. So when I first saw these videos that I've shared today by Henk a month or so ago, a couple of months ago, I immediately kind of like went to this kind of explanation that it's not melting. We know it's not melting because we can see it's not molten. It's not molten. Okay. We can see that it's a kind of like it's been inflated. But what's inflated? Well, if the toroidal moment is going through the sample, we already know that it is able to spin the brass, and we know that from another sample which I have over here, and that is this sample here, which I discussed in my Russian presentation, and I will just pull up the camera, and if it's still working. It's still working. This is good. Okay, I will show you this one, and it's this sample here. And if you recall, there was this flux loop going on, and so the center of the exotic vacuum object, this structure here, this is the toroid. This is the sort of spray out the top, the soft sort of thing, and this is the focus thing. There is spinning around it, and it's not molten, but it's kind of like jelly-like fluid, and you can see this in Hutchison effect sample. So that is kind of what's going on here, and that produced this loop structure here, which you can now see the in and out there. So if I can maybe get the focus better on that. Okay, so this is where the material is trying to get through the brass, and that is where it actually has punched a hole going through it. Okay, so we know that an intense toroidal moment can cause this to occur. So if I zoom out of that, if you're not wibbly wobbly to death like me right now, so we know that it's fluidized the material and done this damage here. And I'm saying that it goes into a flux loop like that. Now, if you have an EVO kind of like bound onto the surface, And maybe it's, you know, it depends on the orientation, actually. And it might be where paramagnetic and diamagnetic and so forth, they end up having alternate orientations, okay? But anyway, somehow it's stuck on the surface like it was on aluminium, although aluminium is paramagnetic, so I believe that it goes flat onto aluminium, and it might not go flat onto a diamagnetic material like brass, the copper and the zinc oxides and the copper oxides. So it might go at an angle. But anyway, let's say it's going onto the surface, either that way or that way. The toroidal moment it's coming out here. So this is going into the surface, and the toroidal moment is coming out of the top of this thing, okay? And it's churning the spin nuclei of the brass, which is all of the copper 63 and 65. They're all spin nuclei. And then 4.11% of the zinc in the brass is a spin nuclei. So that means that some of the zinc is not a spin nuclei. However, zinc obviously melts at a much lower temperature. So that means its electrons bind the metal lattice much less strongly. And it also boils at a very low temperature. In fact, I believe I'm right in saying that, and someone might like to correct me on this, I think it even boils below the temperature of copper melting. So you can have copper as a jelly, but zinc affected by the toroidal moment and maybe a load of, you know, other things going on in there. You may have that almost in a gas. But the outside of the structure, as I was trying to explain to Henk, I believed would have the kind of mesh on it here that would effectively bind the outside together. Okay? So, is that kind of making sense to people? What I'm suggesting is that the outside of our pillow is effectively held together by a mesh of these, like you see on the Hutchison fracture sample there, and on the Lion 2 dual outside edge. And we know that when it is this mesh, one could argue that IR photons are not penetrating the same way into that area, and you know, there are maybe beta particles and X-ray photons, but that we know from how it's doing this churning process on the Hutchison sample, that it is able to kind of semi-fluidized a skin around the outside, but keep it in its kind of like form. It's still the same shape as it's kind of started out, but it's still shifting things around. So it's kind of like, I don't know, it's kind of like a, you know, like plaster of Paris, and then you get like a mesh, and you could build those kind of like wireframe sculptures. It's kind of like, it's all held together, the plaster of Paris, by the kind of fabric or whatever. And then it will set solid when the music stops, when you know, the excitation stops. But it's still held together by the mesh, and the mesh is, I believe, the toroids interlinking to each other. Okay, they have this binding relationship between each other, and but because they are attached to a surface like that, and the toroidal moment is going through into the body of the material, it is causing the material inside to be more fluid, but it isn't held together by the mesh on the outside. And so it becomes fluid, and then it becomes a gas. The outside is a jelly held together by the mesh, and then it inflates, and you end up with this bad boy here, which I think is one of the most interesting things I've seen in science in my entire life. So well done, Henk. So there we go. Now, why would this specific thing occur? Well, I think we have our answer, and I'm going to look at I'm gonna look at some images that I took on the microscope, and where are we? Not there. Here. Okay, so here I think is probably a very, very important image. And that is a scale of one of the channels, which are all effectively a very similar scale, if you remember. Here, they're all kind of like within a ballpark, the same kind of scale. Okay? And this is what it looks like under polarizing filter, and you can see here that this diameter here is about 1.163 microns. Okay, so there is, and as we have seen in Hutchison effect, these triangular cones. Okay, and I've described it in the past that you might have this kind of like, this is our exotic vacuum object, our fractal toroid, and this is the toroidal moment coming out with its precession moment, which can be potentially up to the golden ratio, like that. And that this has an effect at which certain materials will yield. So a lower melting point material will yield and have a soft edge to it. A higher ferromagnetic material like iron has a strong, sharp edge to the event horizon. Okay, but there is a range. Now, if we had something that is, say, a couple of 100 microns, or 100 microns, or 80 microns, that its toroidal moment that's coming out would have only a certain range at which it can churn and produce a liquid and maybe even convert to gas the zinc that's in the material, maybe even the copper, whatever, but churn it around, because we know it can keep it. From the other experiment, this one, we know 100% that this toroidal moment can cause the flow of the brass, but the material immediately adjacent to it is not affected at all. It is not melted at all. So this is a very highly localized effect. And you can imagine that these things sitting on the top of the brass, projected into the brass a certain distance of that thing, and that these are all over the surface, and that fluidized it, maybe made it to gas, blew it up, and you ended up with the pillow 1, and on replication ended up with the pillow 2. Okay, all right. So let's have a look at some more evidence to support this. So I didn't know, and I said, Henk, you've got to send me that sample because I want to look at this under the microscope, because this is kind of like, I believe that this is what happened. Why I say this is Hutchison-like is because we know that ectons are evos. We know that Ken Shoulders produced evos in vacuum chambers and through pulse discharges. We've seen how the fluidization in the alum experiments causes the evo launch point, the nature of the blowing up of the coherent electrons, the fluidized electrons, and the breakup products, those evo self-similar breakup products that we've observed doing work in the high frame rate videos that I've been sharing from the VEGA element experiments. These are all replications of the observation of Ken Shoulders, in my view. And so we know that evos are being produced in this experiment. They're similar to the ones observed by Ken Shoulders. Ken Shoulders are saying those are what caused John Hutchison's effect. We have a metal in John Hutchison's experiments like this one. It would be sitting on a non-conductive surface. The exotic vacuum objects that he is producing are being directed towards, which might even be guided by either magnetic fields or light fields. And they go into the metal, they aggregate, and then depending on whether they are excited at the point of contact or excited by the type of metal it's interacting with, or post-excited once they've aggregated to a certain amount within the sample, then the various effects are occurred. This is directed energy, i.e. the energy is already in the material and you direct what you want to do with it. You're not putting it into a direction. That's like, kind of like a simplicity version of actually what's possible with directed energy. So that is kind of like my broad understanding. So I was very pleased earlier this week to be able to have the chance to look at it under the dyno light, and I was very pleased to find that this is exactly what I believe is happening. And I think that maybe when I've got all these images out to you, you might well agree with my assessment of the situation. Anyway, because this is relatively simple to do, and it is, in my view, a Hutchison effect. It's a skin of exotic vacuum object, toroidal moment, spin nuclei, interaction effect. And so the key point is sorry, I missed it. We've shown from the Vega Valley here that the width of these average channels is around about 1 to 1.2 millimeters. Okay, so if you had a piece of metal here, then that would be what that let's say it's 1.2 millimeters. You're talking at kind of like 600 microns. Okay, and our sample here is metal that's 750 microns. Okay, so EVOs on the surface produced, forming a mesh, projecting their toroidal moments in the reach of the effect of the toroidal moments is enough to fluidize or potentially convert to gas, the zinc in this case, all of the material inside of this, but not sufficient to affect the underside, right? The reach of the toroidal moment. And so that would lead to a pressure building up, but a disconnection from the other side where it's still solid, or it might be encased with EVOs at the bottom, and you end up with a bucking effect. So you have two of the same type, maybe. The whole thing is effectively one type, and they are pushing away. Oh, sorry, they would be round this way, by the way. You would have this bucking effect. And we've seen this bucking effect in other Hutchison samples where, and I've described this a long time ago, where the EVO grows and grows in size until the common poles push the material apart, and it twists like that, and so forth. So I think I can I'm going to put my neck out on a limb and say that this is a Hutchison effect sample, and it's a repeatable process. Okay, so I'm going to look at some of the images right now, and straight off, this is from the Pillow 1. Okay, and you will, I mean, for me, this was just wonderful. I mean, it's just like everything I could have imagined. And I haven't done the stack focusing on this yet, but I will do that so that you will have a fully focused thing. But here we go. Boom. Boom. This is the surface of the Pillow 1. And literally, I couldn't have imagined it closer. But it is made up of these polygonal cells, which are kind of like stacked on top of each other. Okay, and you can see me changing the focal plane here, and these will be stacked. Now look how clear that is. Now, of course, it ends up being oxidized or whatever, and sometimes the oxide comes off, but look at this spot over here as we change the focal plane. Oh my, what does it look like? Oh, what does it look like, guys? That's just amazing. Look at that. Let's zoom into that. What does that look like, my friends? Have we got like the mark of an EVO? I would suggest that we do. Yep. This is the Hutchison effect. It's been done. It has been replicated. Hutchison was not fabricating his things. This is a real thing that can occur, and Henk Jurrien has done it. Okay. Now this is the impact, and you'll see other examples. You can see the boundary here. and the central spot. Okay, and I will actually show you what this kind of looks like on, which is a little bit clearer than this particular image, on aluminium by one Ken shoulders. Okay, it's like this. Okay, so what you're seeing here on the right with the striations around the edge, I don't know whether it's coming through on YouTube's encoding, okay, is exactly what you're seeing here. This central zone, okay, this boundary layer with the striations and the unaffected material on the outside. Yeah, it's a bit like that, Gordon. So he says, is it metal being turned into a metal phyllo pastry? I think it's because it's 0.75 of a millimeter, and because these things that are produced in the parameter space of Henk Jurrien's reactor, the pressure, the residual hydrogen that's generated from the residual moisture in the air, in the residual air, and the field emission and so forth, it just comes together to produce this effect. But I think this is an easy ability for people to replicate the Hutchison effect. Now, what does Ken Shoulders say about this? So this is figure 10. You can see that this is about 20 microns here. So this overall structure is about 20, 40, 50 microns, about 50 microns across, I'd say. So and you can see the kind of hexagonal, it's not so clear on there, but it's more clear on this part of the outside of pillow 1. But what he says here is, another conclusion concerning the order of events can be found by referring to figure 10, the one on the left that I just showed you. This is the backside of a 6 micrometer thick aluminium foil immediately under one of the deposits. What can be seen here is a strike mark, similar to figure 2, which is characteristic of the exit side of an exotic vacuum object strike. It appears that the exotic vacuum object has transited the aluminium oxide and struck the aluminium foil before the aluminium oxide fluid arrived. This is in line with an earlier conclusion that the exotic vacuum object first disrupts the material by passing through the solid, then liquefies it and imparts momentum to the fluid. In this scenario, the exotic vacuum object is what moves the fluid. Guide the EVO and you guide the fluid. So, he is saying that it is fluidizing the material that it is transiting, and that is what is going on, I believe, in this. Henk, congratulations. You have not only replicated Hutchison effect, you've replicated the observations of Ken Shoulders, and you have replicated in sequential experiments the Hutchison effect. This is a groundbreaking moment in history. So let's have a look at a whole bunch more of these images. Why not? Okay. So here we go. Here's another one. So this one's kind of blown off the material on the surface here. In this one, yeah. This is blown off the material. But in this next one here, you can see the central spot. You can see the kind of inner area, and you can see the kind of slightly affected area on the outside. Maybe I need to zoom in. And like I say, I will produce the composite images and you will be able to look at these. You can see clearly we've got the hexagon here around the outside, the central spot, the focal point, okay, and this boundary area here which is affected differently, okay. The other point to note is that this large EVO that came in maybe was protected from penetrating the other EVOs that were forming the mesh that caused this thing to be a jelly. Okay, so the purpose of me going to Henk a couple of weeks ago was to set up a configuration, because what happened was he actually, I think he saw part of the formation of the pillow, but he was so amazed seeing it, he didn't like think to get his camera out and do it. So what we've got for him, and thank you to Charles and others for supporting this, is we have a 12 terabyte drive which can record 60 frames per second at I think 10-bit 422, and it can record that for 9 days. And separately on the computer, it can record the parameter space in a lower quality with a smaller window of the experiment, and then with the time and so on. And he can then go through you can just leave it running. You can see the event has occurred, and you can go through back in time and find the point at which it was not happened, and then after it happened. And then he can go into the extremely high quality 4K 60 frames per second 422 10-bit video and chop out the section of that video where the event occurred. So in theory, moving forward, we can have extremely high quality captures of events. Okay. So yeah. So again, I'm moving through the focal plane here, and that's that one. Again, this is just a look through the focal plane. And what we're looking at here, actually, in this part here, is the top ridge. You can see this kind of ridge that's running along here, this kind of ridge. And that is what I'm looking at here on this part of this image here, the ridge. Okay. And you can see these very geometric structures here, all hexagonal and whatever. Okay, so I will combine these into single focus image. This is with a different color profile, but you can get to see the same kind of things going on. And, you know, this is kind of what you're seeing here. This is where a couple of sections have been blown off. Here you can see something that, you know, maybe you've got the central spot and the polygonal area on the outside. Okay. Again, this is on the ridge area, and I'm changing the focal point. Go back through that. It's lovely. I mean, look at that one down there. I mean, this one on the edge here. It's very, very regular Evo structure. And these like to aggregate. They like to aggregate. They come together. If you remember the macro Evo structure on the line reactor, where you had the two, the yin and the yang, the one side is made of a load of these things coming together in a vortex, if you know what I mean. So the moment of the existing toroidal, fractal toroidal structure pulls in ones of the same type and to aggregate into it. But in the process, you have these ones kind of like semi-orbiting around it and maybe setting up themselves on resonant areas. And so, yeah, it's a thing of great beauty. Look at this. It's just stunning. It's just stunning in my view. Well done, Henk. So, like I say, I will share the raw images. It will probably be a couple of gigabytes, but I will also share the composites in the blog when I've made the composites later in the week. Okay. Here's a view a bit further out. You can see several Evo strike marks here. Maybe I can get them into more focus. No, that's less focus. Here. So there's one clear strike mark after the fact. I think there's another one up here. Yeah, it's like slightly off to the side. And I think this is the underside of the lower plate. So I'm talking about this bit here, that bit. So this is the underside of that bit there. And you can see that it has a couple of central points here. Now, could these, I mean, that looks like it might be a five-sided Evo, and that might have crept underneath between the iron and the brass. You've got another cluster here, slightly bigger. Or it might be the toroidal moment from the top structure punching all the way through to the base brass plate. Whatever, that is what we are seeing there. And there's a couple of images here. This is a close-up view. Again, this is one mark. Okay, so here's some scales. And so we've got ones that are quite small down here. So you can see the 200 micron scale here. And we've got some that are probably 40, 50 micron here. And this one here this is radius of 89, practically 90. So I would suggest that this is 180 across, 180 micron. There's one here that may be bigger. It might just be a merging of a number of them. But anyway, given the fact that this is, let's say, 180 microns across, you can understand that then this would be burrowing into the surface. It's, let's say, D4D. It's 180, then let's say it was 160 microns across. It would be burrowing into the surface. It would be 40 microns on the subtor, and so it would be burrowing into the surface 20 microns. And then the toroidal moment would be coming out from that and affecting the material inside. Okay, so that is all from the pillow one, and I've now got some images that I want to share from the replication, because we're going to learn a little bit more from that as well. So let's have a look. So on the surface of the replication, it has these balls, which we've seen, and again I've got shifting in focal plane, and so you can see how prone they are from the surface. They're really, I'm going back up to the top and back down. Be interesting to see what these are. I think they're probably copper oxide outgrowths, but these are plasmoids that have traveled across the surface, like we have shown in extreme detail, the ecton explosion, the exotic vacuum object, fluidized electrons coming to a launching point. It blows up, and then you have fragments traveling across the surface, and they are fluidizing the copper and potentially converting it to carbon or to iron. And we will find out when we analyze these structures. Some of them are quite beautiful here. These are, in my view, different types of copper oxides growing on the surface as it travels through. And of course, oxygen, in my view, is the most synthesized element in LENR. I know a lot of people talk about carbon, but that's because it stays behind. But the reason I say that is because if you look at the Earth's crust, oxygen, is it silicon or oxygen? I think oxygen is the most abundant element in the Earth's crust. I think that's right. And then silicon, and then aluminium, actually. And then I think it's like, I don't know, something, and then iron or whatever, and then calcium or something. All the sort of things you typically see in LENR, which is why I believe the crust is made by LENR. Okay. So it's either the top or the second, I think. I think it's number one. So if this is copper oxide, people say, oh, it's just oxidized. Well, actually, it might be the fact that part of the copper was converted to oxygen and then it became copper oxide. Okay. But because we're working in residual air. So you can see, if I go to the base focal plane, is it here? You can see the area outside, this is the brass without much effect. There seems to be an Evo strike here and an Evo strike here. But anyway, the fraction of the EVOs have come down here, and they've been churning up this material. Again here, some of these rather nice looking structures, and then panning down, or rather focusing down.
So it does look like we have an EVO here and an EVO here and an EVO here, because we've got these little mounds, these polygonal mounds. If I zoom into that, you'll see it's a hexagonal mound. So it might be that these material around the outside are swept up by the actual EVO that effectively died at this point, and there's another one here. So these might be fractions of a much larger cluster. Now, this is a little blowout hole on the pillow 2, the sequential replication of this Hutchison effect. And we are going to pull focus through into what's inside the chamber. And you can see that it doesn't look oxidized. It looks much more like maybe raw brass. Or copper in there, and that's that. So, and there seems to be some structure in there. So these are the kind of things that I will want to look at under SEM. There appears to be a strike mark here and a kind of regular array around there. So I would suggest that this is maybe something to do with what was going on that produced this thing. So I'm going to do another pull focus, I think, maybe. Oh no, that's just the top of the focal plane that I've decided to take. Okay. So this is, you know, this might have been where another EVO blew up on this very thin surfaced area, and or maybe something got inside and it blew up and it's punched a hole through EVO sort of scale and let the gas out. And I'm looking at the boundary of this part that's blown up here, this part here, this corner part here. Okay, looking at the boundary there. Okay, so we're going to go down the focal plane here. It's quite a distance, and so I've just pulled straight here. Now look, what we're seeing here is again these radial striations with this geometrical edge with the kind of like swept around the outside. This looks very similar to sort of the thing that Ken Shoulders was showing. And so I'm very interested to partially take the structure apart and see what we see under SEM. And there appears to be at this point here, if I can maybe pull the best focus here, a much smaller EVO strike mark here, with the kind of hexagonal outside and the central point here. And I believe that we will find out that this central point may be iron. And if it is, this will be 100% confirmation that the iron is the magnetic core of an EVO. I'm pretty confident about that anyway. But I've actually got a scale here somewhere. There it goes. So in this case, this is about 150 microns across, this particular one. So these ones are rather large. They're getting on for the size of the ones in the Hutchison fracture sample. And so these structures on the outside here, again, this is about 100, 110 microns across. Okay. But I tend to think that these ones, it's actually the EVO that's in the middle. So there was kind of an EVO here, and it was spinning around, and it fluidized the material around the outside. Okay. There was another EVO here, and it fluidized the material around the outside. You get these central spots. And that, my friends, is most of what I wanted to show. For those of you that didn't see the original videos, I will pull up a couple of those now. I will also, you need to go and look at the video where I'm looking at the edge of the alum cathode. And you can see when we get to the edge, these spots that are there that are due to the launching points of where the electrons come from, the sort of bulk of the material, and they come to the center and they kind of fluidize and they come here and they focus. This is what I'm saying, is that can't happen right at the edge in the same way. And I believe that is what leads us to the kind of observations that we have had with this pillow thing here. It's going to
allow me to show you here. This one here. The pillow 1, yeah. And pillow 2, yeah. And the piece of material that was under pillow 1 and that is largely unaffected on the back side of the brass. Okay, so there we go. So let me get those images up. Give me a sec. I can't find it. Silly me. Need more preparation, don't I? Let me have a look at your questions, maybe. Maybe I can find the video for... No, I don't. Okay, all right, I'm going to leave that there for the minute. Right, so I'll see if you've got any questions for me. So what have we got here? Oh, was I on the wrong camera? No, I wasn't showing anything. I was looking for something. I mean, they're launched and stuff on the cathode. But here, let me show you this, for instance. These are on the anode stem of the VEGA experiment. And so you can see the striations here around this beautiful kind of parasol type structure. I love these mushrooms called parasols. They're called bedler here in the Czech Republic. They make fantastic mushroom schnitzel. But you can see that these are ones that have been launched from the launching point on a cathode, and they've come and struck the alumina, not the alumina, the silicon dioxide quartz stem. And so they leave these distinctive strike mark patterns in abundance. And so there are many of these. You can see from different viewpoints here. They've got the kind of flux loop between the two on this one. Very, very many images like this. Here we've got something in the middle, and this could be just matter that's transported or rammed in, or this could be the point of maximum dark matter and transmutation. So here's one that's kind of like, you've got a white area, and this is kind of a bit like what we're seeing on the pillow, where you've got an overall area where you can't really determine what's going on, and then another one's come in and it's done a kind of clear strike mark, and so you get a better idea of what's going on. Here's a very, very nice large structure here. Look at this bad boy. He's a rather nice structure. I don't know why are they smaller? Why is it just gone small on me? I don't know. Okay, that's coming down like lots and lots of them here. Okay, slightly out of focus there.
Very nice one in focus. So these are EVOs that were launched from the cathode, and they tried to get to the anode because of the field, but in between the anode and the cathode there was this dielectric, and they basically impacted to that. Again, you've got like an impact on an old area here. For me, this is one of my favorite ones here, because it has a lot of the smaller ones around the outside, but you can see just how big they can get. So these maybe 20, 50 micron or something, but this is kind of really bad boy going on here. And it really kind of shows the flow and how much it can disrupt the material in the center. Right. Did you see what I was showing you there? Sorry, did I change my camera? Was I talking to myself? Okay, Kevin Andrews saying, is it known how to control what is transmuted to be able to create, let's say, gold or rare? Of course. The number of times since I started this journey, I've been asked to tell people how to create gold. I did that quite some time ago, and the elements that the alchemists were using were the right elements, because this is a yin-yang process. It likes to take whatever it's starting with and it kind of averages it out. And so there is a likelihood based on parameter space like temperature and resonances of various types, maybe phonon, sound, vibration through the material, and the initial concentrations and so forth, and admixtures and so forth. And so, but if it took 50 seconds with the original Parkhomov reaction table calculator to work out that the elements that the alchemists were using were the right elements. And even on the Royal Society of Chemistry, they didn't know why they were using bismuth. But if you take bismuth and you take potassium or calcium, they are the most likely, i.e. they produce the most energy yield, i.e. there's the most desire when you're trying to compress it into a small box, a small volume at the center of this thing here. When you're trying to do that, the thing that's going to be able to do that best gives you the best yield in energy, and therefore those were the ones that were most likely to produce gold. But similarly, they produce a lot of other elements as well. So if you're going to want to produce the gold, you kind of have to have exactly the right temperature, or exactly the right size of particles, or exactly the right size of whatever. But what they were using were the ones that were most likely, under my hypothesis, to produce gold. And it was a very satisfying exercise. I think I posted that as Gold Maker or something. It's on Steam, and I think it was about 4 years ago, or 3 and a bit years ago, because I keep getting asked this question: why don't you produce a lot of gold? Because if you look at the analysis we did of the water flow plasma discharge of Suhas Ralkar when he was making his nickel foil out of nickel sulfate in water in 2017, when he analyzed that, some of the strike marks had gold and even, I think it was palladium, and we had silver in there, like pure, almost pure silver. And so what it is that each of those individual strike marks would have been resonant to produce, in the area they did produce them, from the prima materia and the inputs and the parameter space, the gold on the output. And so someone just has to do a lot of hard work and work it out. And you could probably work out that some people have already done this in the past, but because people don't believe transmutation is possible, they don't try. Mostly people can't be bothered. They want someone else to do it and tell them how to get rich quick. But they can't be bothered to do the work. They just want the money. And that's just reality. But for me, converting plutonium or cesium-137 or strontium-90 into carbon that you can eat is a lot more exciting, because that means we have unlimited energy from thorium and uranium. Thorium is particularly abundant, and we can produce all of the energy humanity needs to use from a known process which is being installed increasingly. There are all types of countries around the world, all kinds of countries around the world that are increasing or extending or otherwise producing more nuclear power. This will produce more nuclear waste, and therefore we need a practical solution to that. So keeping people warm, watered, well-fed, and cold when necessary, and healthy, in my view, is better than a lump of gold. And so that is kind of why I'm focused. And moreover, this technology relatively easily, it would appear, and repeatedly converts these materials into these normal non-toxic elements. And so you don't have to work so hard on establishing the parameter space to just get rich quick. You can focus on fixing the real problems of humanity. It's not so that I've spoken about this before. I think in 2016, long before I got to where I am now, the monatomics, like this monatomic gold that I have here, this white powder gold. This is kind of like the crystal resonant key to producing an element of your choice. It's kind of like one of those experiments where you've got the salt crystals in your preschool experiment where you grow them on a piece of string or something, and you see all the salt crystals. It needs a nucleation point, and I've called this like it's like the birth of the universe. Let's say that occurred, but certainly when there's a supernova, you have all this prima materia, and it doesn't know what to identify as. And you have a Jesus over there, a Muhammad, and a Buddha, and they're all very charismatic leaders, and they have a pattern for how people should live their lives. And the prima materia flock to the various things, and you get a spread spectrum of elements. Of course, the first element that's statistically the first element isotope that's statistically likely to form out of prima materia is a proton, and that's why you get a lot of hydrogen formed. It's more unlikely that you get the resonance for heavier and heavier elements, and so by having monatomics like this, you would add this to assist in the process. Once you converted material to prima materia, this would assist in the organization of the material when it wants to settle down. In the Adamenko experiments, they're starting off, let's say, with 4 nines copper, 99.99% copper. And on their accretion disk, following the electronuclear collapse, which it would appear he came to the same conclusion that there is dark matter involved in the center of in places in his experiment. It plays a role. It certainly had to be considered. That when the material settles down, you get like a blob that's like 83% gold, and another blob in the same experiment that's like 70% lead. And this is the thing that those particular fragments of the overall macro electron nucleus macrocluster, the exotic vacuum objects, this prima materia, when that settles out, the fragments of that, they themselves had their own resonance. And I've described this before, where I believe that if you've got truly coherent subnuclear prima materia and you keep feeding it energy, at some point the cluster size with the fractal toroidal compression will only be mostly able to settle out at one element. Okay? And typically, when people push this to the limit, for instance, in the Claire cavitation and in the work of Adamenko, you end up producing a lot of lead. And in part, that's because it's the heaviest truly stable element, because bismuth is not technically stable. It was a very, very long lifespan. But also, you're pushing the resonance to a point where if it breaks, it gets caught up in another structure that then deactivates it, and you end up with a lot of lead. So you will push towards lead. So you kind of want to get it so that this isn't a case, and I've said this before, this isn't a case of if you want to target a particular element, more is not necessarily better. It's the correct thing that's better. And that is where the work has to come. But I believe there is indications in the historical record of what will promote a thing. So we know this flux can come from the cosmos, and we know that water can bind it. And there was, I think, this French alchemist, and he went to Mexico, and they used these copper bowls. This is what the Mexicans did, the Aztecs or whatever. They used these copper bowls, right? And they put them in the sun, okay? Now, in the sun, that would, let's say in the summer, there's a higher flux of relic neutrino condensates from the universe. The copper is diamagnetic, and because it's a bowl, it will lens the material into the water, and the oxygen dissolved in the water will aggregate these magnetic charges. And what this French alchemist found was that he would take this water back to France, and when he used this water in his alchemy, he ended up by producing a lot of gold. This is how the story goes. But when he tried just normal water, it didn't. Well, now we have an understanding of why that would occur. So if you want to produce certain elements, it's important that what you're starting with, and that not all water is the same if water is going to be playing a principal role. And since we know water contains hydrogen, which is the easiest element according to Shishkin to produce pure ether stream, these string vortex solitons, it needs 2,000 to 4,000 times less, depending on the isotope of hydrogen, than elements starting from lithium to produce the string vortex solitons. The string vortex solitons are the synthetic form of the abundant cold neutrino, relic neutrino condensates that are around us. So you can produce a lot of them from hydrogen much easier than any other element. And this is why, in my view, LENR works better when you're using hydrogen, but it's not only necessary to do that. And then those clusters can then bind to the oxygen that you've also released. And this is why I believe things like Amaza's electrolysis and the process of cavitation going on in the Ultra experiment are so good. The thing about the cavitation in using aluminium is already wonderful. It's paramagnetic, it's highly conductive, it's a single isotope, and it has a spin nuclei, and so it has everything going for it. And it also forms aluminium oxide, and also metals themselves are how should we put this? They are hydrophilic, and this will lead to the production of easy water, and so you would end up with this charge separation. The charge separation spinning in the identified toroidal bubble vortice things that will produce your vortical moment. This will interact with produce the toroidal moment, fractal toroidal moment, and then you will end up with interacting with dark matter. And so that is my hypothesis. So and so a combination of cavitation, which you're going to get in water flow plasma discharge. It's not surprising that it produced silver. It's not surprising that it produced gold. It's not surprising that it produced palladium. But they are absolutely minute quantities. But if you got the process right, you might end up with a scenario where the quantities in a piece of processed material is actually higher than ores by cubic meters. And you could just then chemically reduce it, because the rest of it's water and metals and so forth, and other things you could chemically remove without using horrible things like arsenic or whatever it is. Well, that's interesting you say dark matter is bunk. I would like to see your papers showing that. But whatever, something's going on that's causing it. Okay, I need to stop in a minute because I've got another meeting at midnight. So I'm going to do a review here. I'm just going to have a quick look at what you're saying here. So WP for Truth says, hey Bob, prima materia, would that be equal to something like the seed of creation, sort of speak? I think it's like naive, unformatted energy that wishes to become ordinary matter. Okay, and when you allow for the music to stop and it to settle down, then if you've got some guidance and comfy environments for it to produce particular elements, it will tend to do that. And I believe that's why when you see the plasmoid, or how should we put it, it's the macro quantum object that would have produced the nascent Earth, that would lead to production of gold in, say, South Africa and Australia and so on. And you get these deposits of particular elements, like you get deposits of particular elements on a accretion disk of the Adamenko experiments. And it's a resonant phenomena. So if you go back and look at the O-Lion Nebula that I shared from my Sochi presentation from the original Lion experiment the Lion 2 experiment internals, you will see that there are these blobs which look like they're fractal structures, and on certain points there's another blob which is at a resonant node, which is a substructure of it, that's a different element, because you can see it's a different color from the backscattering from the SEM. And so I'm saying that resonant blob is although it's attached to an overall larger macro object, it is a different element. And so I imagine that the Earth, when it was formed out of a large exotic vacuum object, then and it would have been much smaller then, there were these zones where these particular elements were formed, and then weathering does the rest, and obviously lightning and other processes which we know does transmutation would have produced the variance on the Earth. So Jason Vielberg, could this process explain veins of precious metals inside the crust? Yes. There's okay. So there's the argument that some elements are dissolved somehow, and then they come up through, for instance, quartz, and they leave these veins. I think it's probably electrical influence, or it could even be an exotic vacuum object that is traveling through a material, and it's leaving a trail of different elements behind it, and depending on its resonance and so forth. But these things could essentially happen instantaneously with a large event, or even the formation of the Earth in the first place. So okay, I'm gonna pause for a second and see if I can find these videos. But the videos I've shared are all on the YouTube channel today, of the initial videos that Henk was sending me, which led me to think that yes, definitely, I believe he had a replication of the the Hutchison effect, and then I said, let's go and replicate it, and he replicated it first time. So it's very exciting that this has been achieved. And it's a testament to, you wouldn't have thought to do this and to be able to try and understand it if Hutchison hadn't done his work. So, and Hutchison may not have done his work if it wasn't for the fact that he was studying Tesla. So, we've got a lot to thank these masters and wizards that have existed before us, these thinkers out of the box. We have to thank them for their contribution to humanity, because it is going to facilitate the next great advancement, I believe, in humanity. So let me see if I can find what I'm trying to find here for you. Probably not, and then I'll just do a review. Not having a lot of luck today on my quick finding of things. No, not going to find find it. Okay, I'll just go through the initial material. Okay, so I am saying that the VEGA pillow that you see here, which actually looks like this, started off as a 0.75 micron piece of brass that looked much like that. And this is the bottom piece, and it was stacked on top of each other. So we have the bottom piece here, underneath the V here, and this is the pillow itself. And that exotic vacuum objects from fluidized electrons interacted and formed a mesh over the top surface and potentially underneath this upper brass plate, and because of their scale and the toroidal moment interaction and the thickness, because it's 0.75 of a micron as opposed to like 4 millimeters or 3 millimeters, I think it's, let me see, the original VEGA value is, I'm going to measure it right now, it is, yeah, it's basically, let me zero that, always better if I zero it. It is, where is it? Oh God, it's a bit dodgy this. Okay, that completely didn't work. Zero. Okay, come on. Okay, it's about 3.5 mil. So it's a little bit thicker than the anode from the alum experiments. So that is 3 and a bit mil, and the channels are, the width of the channels are about 1.2, 1.3 millimeters, and so their depth is, let's say, 0.65 millimeters. So that is less than 0.75 here, and so therefore I believe the toroidal moment is fluidizing the brass inside this, as it did in this one, which we talked about, this flux loop one that's part of my Russian presentation here that I discussed in detail. And so that the EVO comes down onto the surface, they form a mesh, as was observed in the work of John Hutchison here, and in the work of Lion, and that this protects the inside, but also it is firing and interacting with the material inside to a degree. But because these are thick things, you only have this thickness here. In fact, I'm going to find out, going back to my SEM, how thick this white layer is here on the jewel. I wouldn't be surprised if it's the kind of same thickness as the material that is protected from turning to a liquid or a gas, is bound together by into a jelly, allowing it to deform but still maintain or be intact, as in the pillow here, the surface, like it did on the HHO exposed indium. And so the EVO comes down, goes 50% into the surface, and where you have this soft cone here, this allows for the the self-organization of the structures over the surface. So you might have something like that, with a couple of them over the surface, where the fields are kind of interacting. We saw these blue-green things on the Vega Valley floodplain, where you saw those like rows of slightly hexagonal green and red polarized material. And they come down onto the surface and they project out their toroidal moment here into the center of the material of the brass in the pillow here, and that leads to the fluidization of that material, and potentially, in the case of the zinc, the gasification of the zinc. Still, the copper is not melted, but it is jellified, and then through a gap like you see underneath here, this gap, and which you can see in Henk's video where he looks inside, the gas it comes out and erupts. But interestingly, at that point, the pressure is released and it just stays in its form. Turn off the power and you end up with this wonderful thing being produced and then replicated here. So based on everything that I'm saying here, this really, really is a replication of John Hutchison, and it's come from the learning from the VEGA Valley and from previous studies that we were done with John Hutchison. And so the theory was that just like we've got a mesh of these yin-yangs all over the surface here of the Hutchison fracture sample and on the jewel, I suspected that that was what was going on, and so I got the microscope out earlier, and this week, or last week, I think it was this week, still this week, and let me find that for you. We showed that we were able to produce images of the what I would call the mesh over the surface here. And as we go through these images, we are changing the focal plane. And then on this one, you can see up here, if we shift the focal plane to that it is a classical EVO strike mark. Okay, we have our striations around the outside, this central area that's largely unaffected, although it is cleaned off of whatever's going on here, and this central node, and that this is equivalent to what was observed by one Kenneth Radford Shoulders here. So this is in my view, the same object type. The hexagonal geometry here is quite clear. Again, proportionally, it's almost identical. So the amount of affected area on the outside is essentially the same as we observe here. This affected area in here. Unfortunately, the contrast on this doesn't show the central point on here, but of course this has been observed by him and other authors like Matsumoto, etc. And he says that another conclusion concerning the order of the events can be found by referring to figure 10. This is the backside of the 6 micrometer thick aluminium foil immediately under one of the deposits. What can be seen here is a strike mark similar to figure 2. Should we look at figure 2? Where is figure 2? Figure 2 is not that figure. It's figure 2. So this is a strike mark. So this is the EVO going in, and what we're looking at is the backside here. Where is it? Down here. Okay, so that's the backside, which is characteristic of the exit side of an EVO strike. It appears that the EV is transited. So one might think that this is an EVO coming from the inside out, which is an interesting thing to consider. It appears the EV has transited the aluminium oxide and struck the aluminium foil before the aluminium oxide fluid arrived, which is an interesting thing to think about, aluminium oxide fluid. This is in line with an earlier conclusion that the EV, first exotic vacuum object, first disrupts the material by passing through the solid, then liquefies it and imparts momentum to the fluid. In this scenario, the exotic vacuum object is what moves the fluid. Guide the EVO and you guide the fluid. Anyway, so I believe that this is a one-for-one replication of what was observed by Ken Shoulders, and he discovered exotic vacuum objects by, in a vacuum chamber, producing exotic vacuum objects and striking various samples in the study of John Hutchison's work. Okay, that is why I believe it is safe to say with relative certainty that this is a replication of the Hutchison effect, and it's a subsequent replication of the replication of the Hutchison effect was done with the Pillow 2, and this is a repeatable experiment that can be conducted. And here again, we've got a strike mark, but it's slightly different. It has this cleaner section in the middle, the hexagonal area around the outside, and this slightly affected zone. Same kind of proportions as you can see here, and this will be a pattern that will repeat as more people replicate this, I guess. Yeah, so that's a little bit more in focus here. It would be nice to be able to capture some of these zones. Hopefully I haven't damaged them. I'm trying to only contact on the edge, and we'll be able to see the elemental proportions as you go across this. That's the back side of the lower plate, and here's the scales. So from small, sort of, I guess, 25 micron across, or maybe 50 micron across down here. This is 100 micron. This is 160, 180 microns across. Maybe one's a bit bigger here. But again, these are all at a scale that you can imagine their toroidal moments would not liquefy the other side of the brass plate, and that would lead to the pillow formation. And as I said, it could be a case of the whole thing is wrapped in exotic vacuum objects in a mesh, and that they build. They're liquefying using their toroidal moments that are bucking, and as they get bigger and bigger, they then start pushing apart like this. And so that's kind of what happens. And I will pull up the Pillow 2 data here. Just run over that quickly again. So we've got structures on the surface which look like they are formed by plasmoids or exotic vacuum objects. We've got the centrus point here and the kind of fairly geometric structure around the outside, and then the fluidized material around the outside of that. And you see this pattern repeated. So they've got a center point here. Maybe it's not clear to you, but got a kind of center point here, area around here, and the fluidized bit there. Here, kind of center point, central bit, and then the fluidized bit around the outside. And in the Vega Valley, it's where you would see remember I showed you that one where it was copper and zinc oxides around the outside, but in the center we had the iron crenellated sphere. I would suggest that maybe this spherical looking object here was here in the core of the ball lightning, and this might actually be an iron crenellated sphere when we look at it under much better tools. You can see them maybe down here, that this is again probably an iron crenellated sphere here. The core of ball lightning, the core of the exotic vacuum object. And I said here that this looks like it may be copper oxides, but oxygen is if not the second, I think it's the most abundant element in the Earth's crust, and therefore, as I say, that the Earth crust is the signature of what Lena likes to produce, I wouldn't be surprised if that is actually the oxygen in this copper oxide is actually produced by the Lena process. But we can't say it is, because there's oxygen in the tank from the residual air. Again, we've got a regular array here with a lump in the middle and the stuff around the outside, and you're going to get to see this quite a lot, I think. Again, here there's quite a lot. So you've got all this disruptive material around the outside, and then you can see here we've got the thing in the center with disruptive material around the outside. Here in the center, disruptive material around the outside. Here it's hexagonal, this is hexagonal, and they've got the material around the outside. And these would be the subquanta of the exotic vacuum object cluster that you see blowing up in the recent videos that I've been sharing, in my view, of in the Vega alum experiments that we conducted when I was there a couple of weeks ago. Okay. Again, you can see here this is a semi, polygonal, and then the material swept around the outside. This is a small blowhole, and I'm zooming down into the center under here, and maybe the structures that are under here cause this to occur. And I do some more. And now this is the edge blowout area, which is here. And this edge little blowout here, and you can go back to the beginning of this presentation. You can see the detailed images that we shared of that, and I'm going through the focal plane here. And the interesting thing is it has these large structures which have a tight boundary. Okay, here maybe this is some structure there, but we've got a fairly clear one here. Is it? I'll get this one here. So it has the kind of hexagonal outline with the central point, and I believe potentially that we will find that this darkened structure here will have a bit of carbon around the outside, maybe some silicon, and then this will be an iron crenellated microsphere in the center here. So I think we even have a scale for that at some point. So this is maybe approximately 150 microns across, and so you can get an idea that the what I call the magnetic core of the EVO, which when this is formed, like in the Adamenko experiments and so forth, you can imagine that thing that I showed you in that previous video recently, it's hollow inside there, and that's where the dark matter does the transmutation. But the overall thing isn't really formed until the exotic vacuum object collapses, and the material comes back into our reality, as it were, and depending on the resonance and the intensity of the effect, the amount of material then manifests itself back in to our our reality. So yeah, I expect this probably is a crenellated iron microsphere, silicon around the outside of that, carbon around the outside of that, and then it'll just be the copper oxides and so forth. So, and that is the scale of one of these balls on here. And then this is what I was talking about, the channels in the Vega Valley. This is with no specular, and you can see that it's around about 1.1, 1.2 millimeters across. Okay. So thank you very much. This was the Vega pillow and the replication thereof. I'll just see if you've got any questions, and then I will say goodbye because I've got to prepare for my next meeting. That's interesting, Glass Chappie. So he says, Pillow 2 looks so much like a Muranese flat glass pattern. Excellent. So yeah, I want to congratulate Henk Jurrien for this serendipitous but inspirational experiment. This is obviously, you know, John Hutchison did replicate his own effect. Like, he did create a number of samples that look like this. Yeah. So, you know, he did replicate it, but in this particular instance, you know, when he showed me this pillow thing, it was like, well, I'd love to talk about it, but let's see if we can replicate it first. And he replicated it, and they said, right, now we need to replicate it and capture it completely on camera at high frame rate, beautiful resolution. And so that is what we're targeting. But as I was able to get access to these samples and now look at them under the microscope, I think it confirms exactly what Ken Shoulders was saying. It confirms what we've seen in Hutchison effect and other Lehner experiments. This is how it works. And so you can see how you can create weird effects by bucking magnetic fields and the way that they interact with material, either causing the matter to collapse or causing it to fluidize or causing it to transmute, gellify, and so on. But also the fact that it can form these meshes that protect the skin of the structure that it's on. And so that is really interesting to consider. And you know, and I would imagine, you know, that there's this anecdote by Ralph Ring when he was working on the TL car thing, this guy that had some connection with Tesla and they made some sort of anti-gravity craft. He said that when he first went up there, they had this equipment and they had this aluminium sort of model in front of him, and he turned it on, he could feel this cool wind, well, we know what that is now, and he was able to push his hand into the aluminium and it was like jello, and it went round his hand. And this is Ralph Ring. You can go and find this. I think it's Old Man Talks About blah blah blah. You can go and find this video probably on YouTube. And it's another one of these cases like George Eagley told me in India, where the ball lightning came down, it touched the aluminium frame of this Hungarian train, and then for about 20 minutes he was able to manipulate the aluminium there because it was turned into a kind of like a putty jelly type stuff. And this is also what Alec Pizarro experienced when he went to grab a formerly glowing, momentarily before glowing piece of aluminium bar stock, something like a bit like this, that was exposed to the Hutchison effect, and he ended up sinking his fingers a distance into that and smearing it and leaving his fingerprint in the aluminium. And so this is a real thing. This is what happens. And so we've seen the jellification in indium, but it's glowing like it's incandescent light bulb. Obviously something weird's going on there. But this is really, for me, a huge moment in history, a replication of the Hutchison effect. It's compliant with all of the claims of Ken Shoulders, and it was back-to-back replicated. So I would like everyone in their own metaphorical world, or literal, to give Henk Jurrien a big clap. Ken Shoulders for telling us, the basics that we need to know to be able to decode this, and John Hutchison and Nikola Tesla for giving the gifts that they did to get us to this point of relative certainty. So I would like to say thank you very, very much for your time. And I will look through any questions and maybe answer them during the week. If you want to ask me any more questions about this, please go to remoteview.icu onto the blog for this, where I will be updating with some of these images and download links for the video, for the microscopy that you can look at. And when I get a chance, I will be analysing these under SEM, and I will be sharing the data for that as well. So keep a lookout for that. But yeah, I think it's getting quite settled now, so we can kind of move forward with certainty. And I really have to thank Henk again for sharing the setup that has achieved this, because I think as simple as his setup is, I think this effect can be achieved with even simpler setups. And I think it's gonna be, it's going to be another one of those cases like the Ultra experiment, and like another one that's coming up by Chris, who's been using the striking arc of a TIG welder, which we're going to be analysing in California soon, where he's been able to create exactly the same magnetohydrodynamic structure using a TIG welder onto titanium inside a bagel coil that was produced by the a Mars gas on a 10 yen coin and a Mars gas on a tungsten rod. So this is all the same effect. It has this moment that goes in and around, and there's a loop that comes forward and out, and it appears to be magnetic, but I think the flux loop is something to do with dark matter, and that's going to offend people, but yeah, so what? And it's in the other plane, and so you've got in, around, and that way. I think I want to lay that out there, but I expect we'll see the same kind of transmutations as we have observed when tungsten has been interacted with a Mars gas, and when we replicated the same transmutations with David Boutilier's experiment replication in Canada that was tested in Alan Goldwater's Magic Sound Lab. So it's really quite exciting. So there we go. This was Vega Pillow. Thank you very much. Buenas noches, dobro noc, buenas era, good night.